Have you ever found yourself wrestling with an AI-generated image? Desperately wishing you could just maybe move that object a little to the left, or maybe tilt the camera view without the whole thing just falling apart?
Oh, absolutely.
Yeah.
Super common frustration, isn't it?
Yeah. You get this incredible, often photorealistic output, but then trying to do any precise editing afterwards becomes a real nightmare.
Exactly.
Well, today on AI Paper Podcasts, we're diving into a brilliant new paper that's aiming to solve precisely this problem. It's called Generative Blocks World, Moving Things Around in Pictures, by Vaibhav Vavila and the team.
Yeah, this is a really interesting one.
Feels like a pretty crucial step forward for anyone working with generative AI, especially for creative stuff or, engineering applications.
That's spot on, because these large generative models, they're phenomenal at creating stunning images, sort of out of nothing, right?
Right.
But their Achilles heel, really, has always been that precise post-generation control. If you try to tweak specific things, like the geometry, the lighting, even just the camera angle, you often end up with, distortion.
Yeah, things get weird.
Or worse, the object you're actually trying to edit just completely loses its identity. It stops looking like the thing it was supposed to be.
Right.
So this paper, Generative Blocks World, it introduces a really clever way to bring that kind of granular control, the sort of thing we expect from traditional 3D rendering, into the world of AI generation. But crucially, without all the incredibly complex manual setup that usually involves.
Okay, that sounds promising. So for everyone listening who needs the super quick version, here's a 1-minute summary for a short form edit. This paper introduces Generative Blocks World, which is a really groundbreaking approach to 3D-aware image editing. The core idea: it represents complex scenes not just as flat pixels, but as these flexible assemblies of simple 3D primitives. Think of them like AI-native building blocks. And this shift allows for incredibly intuitive manipulation. You can move entire objects, you can adjust specific parts, or even change the camera viewpoint, all while keeping the image looking realistic. A key innovation here is something they call the texture hint, and that works together with a confidence mask. These interact with a depth-conditioned generative model, in this case, FLUX. This combination is ingenious because it ensures that the appearance and the object's identity are maintained, even after you make pretty significant geometric edits. The bottom line: this method dramatically surpasses previous attempts in visual quality, how editable things are, and its ability to generalize to new compositions. It offers a level of precise, structured, and genuinely editable image synthesis that we haven't really seen before. Okay, let's unpack this a bit more. Why is image editing so notoriously difficult in these, really powerful generative models we have now?
I mean, these models, they clearly learn some incredible stuff about scenes intrinsically, like normals, depth, how light should look.
Yeah, they have a lot of implicit knowledge.
But the moment you try to actually mess with the geometry or just shift the camera angle slightly, the image just kind of destabilizes, doesn't it?
It does. It's fragile.
It feels like trying to perfectly re-sculpt a digital painting that was never actually built as a 3D model to begin with.
That's a perfect analogy, actually. And the paper, it really pinpoints 2 core challenges here.
Okay.
First, when you shift the viewpoint, right, you often reveal parts of the scene that were hidden before. They were occluded.
Right, behind something else.
Exactly. And the model then has to somehow magically extrapolate what those hidden textures should look like. That's an incredibly complex task, and it's really prone to inconsistencies.
Yeah, I can imagine. Like guessing the wallpaper behind a moved sofa.
Precisely. The AI is trying to guess what's behind that wall you just teleported away. It's tough.
Okay, so that's one challenge. What's the second? The second is more about us, the users. Trying to directly edit something as abstract as a depth map. Well, it's just incredibly difficult to do intuitively.
Yeah, like fiddling with a grayscale blob.
Exactly. It's like trying to sculpt a statue by only adjusting a grayscale image of its shadows or something.
Yep.
It just doesn't translate well to how we naturally think about moving or changing objects.
Yeah, that makes sense. And the paper even mentions this sort of almost deceptively simple, idealized pipeline of just projecting texture onto a depth map, adjusting it, and then reprojecting. It sounds like it should work.
It sounds logical, yeah.
But they explicitly say it breaks down in practice. Why is that simple idea so hard to get right in reality?
Well, it breaks down because of those very challenges we just mentioned. Traditional methods often fail precisely at that texture extrapolation step for the newly revealed bits. Or they introduce really bizarre artifacts when you try to manipulate the depth without having a true understanding of the 3D objects involved. It's like trying to perfectly patch a hole in a sweater when you don't have the original yarn, or maybe even the original pattern.
Right, the new patch just, it won't quite match.
Exactly, it stands out. So to finally get around this, the paper's central concept, their big idea, is to represent scenes not as flat images or even just a messy cloud of points.
Okay.
But as, and this is their term, small assemblies of meaningful parts or primitives.
Primitives, okay, like building blocks.
Kind of, yeah. And this idea isn't completely new in computer vision. It actually has pretty deep roots.
Oh.
Yeah, think back to like Robert's Blocks World from the 1960s. That was super early AI vision work where scenes were just simple cuboids.
Right, I remember that. Very basic shapes.
Exactly. Or maybe Biedermann's genons theory from psychology, which suggested humans recognize objects by composing them from a small set of primitive shapes.
Interesting connection.
The breakthrough here with Generative Blocks World is that it doesn't just use simple geometric shapes like cubes or cylinders. Its learned primitives are far more complex, more nuanced. They're capable of actually capturing the geometry of realistic, in-the-wild scene elements.
So they're like intelligent, adaptable Lego bricks, but designed by the AI itself.
That's a great way to put it. Intelligent, malleable Lego bricks for AI scenes.
And the real genius, it seems, is that the goal for these AI Legos isn't just to exist, but to approximate the scene's depth map so well that it enables something they call view-consistent texture projection.
Yes, that's the key phrase.
That sounds like the secret sauce, right? That's what lets you preserve the original look and feel, even when you drastically change the camera view or, pick up and move entire objects or just parts of them, all while keeping that high-fidelity appearance.
Exactly right.
I mean, if you've seen Figure 1 in the paper, those cat edits are they're kind of mind-blowing.
They are pretty impressive.
You can translate the whole cat, you can move the ball of yarn right in front of it, you can even scale up the cat's head, and it just works. It looks seamless.
It does. And that's possible because they're exploiting some really advanced techniques for what they call primitive fitting.
Primitive fitting, okay.
Which is essentially teaching the AI how to accurately break down any given image into these fundamental shapes.
Yeah.
And by doing that well, Generative Blocks World enables this precise, structured, and genuinely editable image synthesis.
So it's moving beyond just pushing pixels around.
Way beyond simple 2D pixel deformation.
Right.
This gives you a much more robust, intuitive 3D understanding of what's actually in the scene. It really is a game changer for control.
So how does Generative Blocks World actually do this? How does it pull off this magic?
Yeah.
They lay out this really clever 4-stage pipeline.
Mm-hmm.
First, it extracts these fundamental primitives from basically any input image. Then, it uses those primitives and maybe a text prompt to generate the initial image. Stage 3 is where you, the user, come in. You can intuitively edit those primitives, move them, scale them, or adjust the camera viewpoint.
Interactive part.
And finally, Stage 4, the system generates a brand new image based on your updated scene setup, but, and this is crucial, preserving the texture and the look from the original image.
Exactly. Let's maybe dig into that first stage a bit, the convex decomposition for primitive extraction.
Yeah, let's do that. How does it find these blocks?
Okay, so what they've done is essentially teach the AI to see an image, not as a flat canvas, but as a collection of blended 3D convex shapes. Think of them like organic rounded blocks rather than sharp-edged ones.
Okay, convex shapes.
They use a neural network, building on some prior work like CVXNet. And this network basically learns to define these shapes. It learns functions that tell you if any point in 3D space is inside or outside one of these learned primitive shapes.
Using things like SDFs, sign distance functions.
Exactly. They use SDFs derived from log_sum_x operations to keep everything differentiable, which is key for learning. Then they convert that into a soft indicator function using a sigmoid.
Got it. Differentiable is important for training with gradients.
Absolutely. And what's particularly clever here is that they train different versions of this model to extract varying numbers of primitives.
Oh, interesting. Why?
So you can choose your level of detail. You might want a model that finds just a handful, say 4 or 8 primitives, for really coarse, broad changes. Or you could use a model trained to find, say, 72 primitives for much finer, more detailed edits on smaller parts of the scene.
That's flexible. Okay. And how is this trained?
They train this system on a huge data set, 1.8 million images from LAI on. And they use ground truth depth supervision derived from state-of-the-art depth estimation tools like Depth Anything v2 to help the AI lift these 2D images into 3D point clouds and understand the geometry.
Wow, 1.8 million images. That's substantial.
It is. But the process is surprisingly efficient for something this complex. Training takes about, say, 40 to 100 minutes on a pretty beefy GPU like an A40.
Okay, that's not bad at all for training. What about using it? Inference.
Inference is fast. Extracting and rendering the primitives from a new image takes just 1 to 3 seconds.
Wow, okay. That's definitely usable.
Yeah. And they found that using primitives defined by 12 faces, 12-face polytopes, gave a good balance of accuracy and efficiency, helping them capture the nuances of real-world objects, even in tricky, unconstrained, in-the-wild images.
That's an incredibly robust and fast primitive extraction step. So, okay, the system has ingeniously broken down the image into these fundamental 3D blocks. The next puzzle is, how do you actually use those blocks to generate a completely new image that still looks like the original, just edited?
Right. That brings us to stage 2. Depth-conditioned in-painting and rectified flow transformers.
Okay, sounds technical. FLUX you mentioned.
Yeah, FLUX. They selected FLUX, which is really a state-of-the-art generative model based on something called rectified flow.
Rectified flow. Okay. How does that work, roughly?
Think of rectified flow as a very efficient and stable way for an AI to transform simple noise like random static into incredibly realistic images. It follows a straighter path during generation compared to traditional diffusion models.
Okay, more direct.
In essence, the system starts with a kind of blurry, noisy blueprint of your target image. Then, the crucial part is how it uses the depth map that's derived from those primitives we just talked about.
Ah, the depth map from the blocks.
Exactly. That depth map gets encoded into a compact, abstract form, what we call a latent representation. And this latent code acts as a powerful guide during generation. It's concatenated, sort of glued together, with a noisy image blueprint.
So it steers the generation process using the 3D shape?
Precisely. It provides tight control over the generation. They even used a specific version of FLUX to 1 depth, which lets you tune how strongly that depth map influences the final image using a LoRa weight. That's super useful if your primitive abstraction is maybe a bit too coarse for very fine details you want the image model to handle.
Gotcha. So you can balance the structure from the primitives with the detail from the image model.
Exactly. The AI then iteratively refines this noisy blueprint using its transformer architecture, which is really good at understanding relationships across the image to predict the necessary changes step by step, eventually arriving at the clean, final, edited image.
Okay, wow. That's sophisticated. Now, for me, this next part is where it gets really interesting. The true secret sauce, the thing that allows for such incredibly robust editing and texture preservation, even when you make massive geometric changes, it's this thing they call the texture hint.
Yes.
It feels like the ultimate workaround to those big challenges, like filling in hidden areas that we discussed earlier.
It absolutely is. The texture hint image, which they call XINT, combined with a confidence mask, is genuinely groundbreaking for this task.
Confidence mask.
Okay, because traditional texture preservation methods, like maybe just caching pixels from the original view and trying to map them over, they just fall flat, especially when you're making major camera moves or large manipulations of the primitives. Figure 6 in the paper shows this pretty clearly. Those older methods just can't handle it. Things go wrong.
So how is this hint generated?
It's generated by this clever method they call point cloud correspondences. Imagine this system taking the 3D point cloud from the original view and the point cloud from the new edited view after moving primitives or the camera.
Okay.
It then figures out which point in the new view corresponds to which point in the old view, even if primitives have been scaled, rotated, or translated. It robustly finds these matches.
Ah, so it tracks where each piece of the surface went.
Exactly. Then, using these correspondences, it projects the pixel colors from the old view onto their correct new positions in the new view. This creates the XINT image.
The texture hint.
Right. And this hint is then fed into the generative model, essentially telling it, okay, for this part of the moved object, here's the texture it should have. It ensures the texture moves with the primitives.
Brilliant. And the confidence mask, what does that do?
Equally important. The confidence mask, OM, basically tells the AI which parts of that linked image it can actually trust.
Ah, okay. Why wouldn't it trust some parts?
Well, think about areas near depth discontinuities, like the edge of an object against the background.
Right.
Those areas often get low confidence. Why? Because those are exactly the spots where new texture might need to be revealed if something moved away, or where old texture might become hidden if something moved in front. The hint is unreliable there.
Got it. So the mask flags the uncertain areas.
Precisely. And then the generative model, the FLUX model, takes on this kind of denoising role, which isn't just removing noise, it's really about intelligently interpreting this raw hint. It cleans it up, it fills in any gaps where the confidence was low, and it refines blurry textures so everything looks perfectly coherent and realistic in the final output.
Wow. So it uses the hint where it's good and uses its generative power to fill in the rest.
That's a perfect summary. They even do a pre-processing step where they fill in those low confidence regions in the hint image before feeding it to FLUX using something like Voronoi inpainting, just to maintain local color consistency and give FLUX a better starting point.
That's clever. And is this hint generation fast too?
Yeah, surprisingly fast.
Yeah.
Generating the hint and the correspondences takes about 1 to 2 seconds. And then the final FLUX denoising or generation step takes only about 3 seconds on a powerful GPU like an H100.
So the whole edit process is like under 5 seconds?
Roughly, yeah. Which is incredibly fast for the level of complexity and the quality of the results. You know, thinking about it, Generative Blocks World really has some incredibly attractive properties that make these primitive decompositions so powerful in practice.
Like what?
Well, first, they're genuinely selectable. As a user, you can intuitively pick and manipulate individual primitives. We saw that clearly in the cat example in Figure 1, right?
Yeah, moving the head or the body.
Second, they are remarkably object-linked. The segmentation you get from the primitives often aligns beautifully with distinct objects in the scene, or even specific parts of objects.
Ah, so a block often represents a whole thing or a meaningful part of a thing.
Exactly, which means you can move an entire object, like the whole cat, or just a specific part, like its head, while keeping its identity intact. Figures 1, 3, and 4 really highlight this object level or part level control.
Okay, that's useful.
Third, and this is absolutely critical, these decompositions are highly accurate. The depth maps you can derive just by rendering these primitives are strikingly close to the actual depth of the original scene.
And that accuracy is key for
making the camera moves look right, and for generating those crucial texture hints accurately. If the geometry was wrong, the hint would be wrong, and the edit would fail. You can really see this visual fidelity in Figures 2 and 5.
Right, accuracy enables consistency.
Precisely. And finally, the fourth property is variable scale. This is really powerful. You can represent the same scene with a different number of primitives.
The K parameter, right?
Exactly, K. Use fewer primitives, like K8, for coarse, high-level edits that affect larger parts of the scene. Or crank up K to, say, 60, for incredibly fine, intricate adjustments on smaller details. This flexibility is shown off really well in Figures 7, 8, and 12.
That variable scale feels like a huge differentiator. It offers a level of control granularity that we just haven't really seen before in these kinds of editing tools.
I agree.
And when you compare Generative Blocks World, or GBW, to existing methods, its advantages really seem to leap out, don't they?
They do.
Like, take the point-based methods, drag in or drag diffusion. They were cool, very intuitive for dragging pixels.
Very direct manipulation.
But GBW offers true 3D understanding, right? The paper shows that example in Figure 4 trying to move a clock with drag diffusion.
Yeah, the clock example.
And the clock just sort of warps and loses its details. Because it's just deforming pixels, it doesn't know it's a 3D clock.
Exactly. It lacks the objectness.
Whereas GBW infers these actual 3D primitives that represent the clock, and you manipulate those. So it maintains the geometry, the scale, the texture much more faithfully.
That's the core difference. It operates in 3D.
And how about compared to methods that do use 3D priors, but maybe only for single objects like StyleNerf or Dream Fusion?
Well, the big advantage of GBW there is that it generalizes much better to a complex, multi-object, scene-level editing. It's not just designed for isolated objects. It can handle a whole environment.
Right, it decomposes the whole scene. And what about other primitive-based methods? I think the paper mentions loose control and build a scene.
Yeah, it compares itself quite favorably to those two. The key advantages seem to be superior depth accuracy from the primitives, which we already talked about.
Crucial for realism.
Crucial. Plus, GBW doesn't require time-consuming fine-tuning of the main diffusion model for every new scene or edit, which is a big practical win.
That's huge. No per scene optimization.
Right. And maybe most importantly, it supports those full camera moves robustly because of the texture hint mechanism. Figure 5 illustrates this really vividly.
The one with the apples and the duck.
Yeah. With loose control, the paper shows that a camera move might bizarrely make the number of apples change, or suddenly add extra ice cubes to a glass of water, or spawn more ducks.
Oh, wow, okay. So it hallucinates changes.
Kind of, yeah. Whereas GBW, in those same examples, consistently shows the exact same scene content, just viewed from a different angle. That texture hint really holds things together. And, this isn't just about subjective visual comparison, like, oh, this one looks better. The paper actually backs this up with strong quantitative results.
Table 1.
Exactly, Table 1. It shows Generative Blocks World significantly outperforming loose control in metrics that measure both geometric consistency.
So how well it preserves the actual 3D shape and structure.
Right. It has lower error there. And also in texture consistency metrics like PSNR and SM.
Which measure how well it maintains the visual details and appearance.
Exactly, so it scores higher there. It's strong evidence that GBW holds tight to both the underlying geometry and the original look of the source image, much better than prior work.
That's compelling. Let's maybe walk through some of those examples from the figures again, because they really do bring this whole thing to life.
That was good.
The cat example in Figure 1 is such a fantastic opener, isn't it? You see the original image, then you see the underlying primitive decomposition, those colored blocks fitting the cat.
You see the structure.
And then the sequence of really impressive edits. Translating the whole cat left then right, moving that ball of yarn right in front of the cat while also shifting the camera slightly.
Yeah, the yarn edit is great.
And even scaling up just the cat's head. Each edit looks incredibly seamless. It maintains the cat's integrity, the fur texture, everything.
It really demonstrates the part-based control.
Or like the Red Mustang example. You can clearly see the intricate depth map derived from the primitives and how those primitives manage to decompose the car's complex shape quite well.
It handles curved surfaces surprisingly effectively.
And those camera moves in Figure 5, we touched on them, but they're particularly convincing. Whether it's the apples on the table, the glass of water with ice, the duck in the pond, or those rocks, GBW just consistently keeps the scene's content intact as the viewpoint shifts.
Yeah, it's a stark contrast to the other methods shown there, which struggle to preserve things accurately.
And then there's that variable scale editing, Figures 7 and 8. This is really neat. At a coarse scale, like with K6 or K8 primitives.
Fewer larger blocks.
Right. Moving one of those big primitives affects a large part of the scene. Like in Figure 7, adjusting one block changes a whole chunk of the dog's fur texture.
Broad control.
But then you switch to a finer scale, K24 or even K60.
Lots of smaller blocks.
And suddenly you can perform these incredibly detailed edits, like subtly scaling just the specific light blue or green primitives on the dog, or precisely translating that small dark blue primitive in Figure 8. It gives you that zoom-in control.
It really shows the power of hierarchical representation.
It's also quite insightful, I thought, to see how the confidence mask actually works in Figure 7. You can literally see it highlighting the holes or the low confidence regions near the boundaries of a primitive when, for example, a dog primitive is moved away.
Yeah, it shows you exactly where the model needs to synthesize new information.
Right. It reveals what was previously hidden behind the dog. And what's truly impressive is the ability shown later, I think, in Figure 8's bottom rows, to compose multiple edits together.
Stacking edits, yeah.
Move this, scale that, change the camera. And while it seems generally very robust, the authors are honest and note that stacking many really complex edits can sometimes push the limits a bit.
Right, there can be challenges.
Like sometimes the texture preservation might show tiny inconsistencies, maybe a tiled floor pattern appears that wasn't perfectly consistent with the original perspective after many changes. But overall, it seems remarkably solid.
Yeah, it holds up very well under complex scenarios. Which naturally raises an important question. What are the current limitations of Generative Blocks World?
Good question. It looks amazing, but nothing's perfect.
Exactly. While it's incredibly powerful, it's not quite a magic wand for every single scenario yet.
Okay, like what?
Well, objects that have complex internal structures or holes, think about the empty space under a chair, or maybe the handle of a coffee mug.
Topology issues?
Kind of. Those can still be challenging if the convex primitives don't perfectly model that negative space. It might sometimes require using more primitives, making the decomposition finer, or perhaps incorporating some additional explicit segmentation information.
Okay, so complex shapes with holes are tricky. What else?
Depth of field. If you have an edit that brings an object that was way out of focus in the background into sharp focus in the foreground.
Right, changing the focus plane dramatically.
Exactly. The AI might not perfectly replicate the change in blurring or bokeh characteristics. That's a subtle photographic effect that's hard to model perfectly during these kinds of edits.
Makes sense.
Similarly, while it handles translation and scaling well, extremely large object rotations can still sometimes lead to results that are less than perfect. Figure 9 hints at some of these challenges, though they don't show extreme failures.
Okay, so big rotations are still tough.
And in a practical interactive workflow, a user might occasionally need to give a little manual nudge or tweak to the confidence masks.
Oh, why?
Well, imagine an unwanted reflection on a shiny object. If the reflection doesn't quite move perfectly realistically when the object's primitive is moved, manually lowering the confidence in that reflection area might help the model regenerate it more plausibly in the new position.
Ah, okay. Little interactive refinements might be needed sometimes.
That's potentially for perfection. Another interesting point they raise is about real-world images. While the system can extract texture hints from real photos, the absolute most pristine, artifact-free edits tend to happen when the edited image generation starts from the same underlying noise tensor and the same text prompt as the original source image generation.
Ah, so starting from a generated image works best.
It seems to currently, yeah. This highlights an ongoing need in the field for even better image inverters tools that can perfectly translate a real photograph into the AI's internal lighting representation. That would make the whole pipeline even smoother for editing your holiday snaps, for example.
Right, bridging the gap between real photos and the AI's internal world.
Exactly. And one final really fascinating challenge they mention is when a geometric edit directly conflicts with the text prompt you provided.
Oh, interesting. Like what?
Imagine your prompt says a red cube on a table, and then you use the primitive editor to geometrically delete the cube primitive.
Uh-oh. What happens?
Well, the AI can get confused. The geometry says no cube, but the text prompt insists red cube. This conflict can lead to the model trying to inpaint the missing region with weird, unharmonious content, maybe trying to faintly suggest a cube that isn't there. Figure 10 shows a brick example like this.
Huh. So geometry and semantics can fight each other.
They can. Sometimes you might resolve it by also editing the text prompt to match the geometry, a table. But it highlights this delicate interplay between the visual structure and the language description that these models are grappling with.
That makes a lot of sense. It's a complex system. So looking ahead, what kind of future work directions are mentioned in the paper? Where could this go next?
They have some interesting ideas. One is maybe applying these point correspondence calculations, not just at the end to create the hint image, but actually within the network layers of the generative model itself.
Injecting the correspondences deeper?
Yeah, maybe into vital attention layers or something. The idea is that this could lead to even more robust solutions, embedding the geometric consistency right into the generation process.
That sounds promising.
There's also the really complex challenge of trying to properly account for view-dependent lighting effects.
Ah, like how shininess changes as you look from different angles.
Exactly. Specular highlights, complex reflections, iridescence. Those things change based on viewpoint, and modeling that during edits is a whole other level of realism.
Definitely a hard problem.
And thinking about broader applications, a huge next step would be enforcing temporal consistency across frames.
For video.
For video, exactly. If you could apply these kinds of edits consistently over time, you could generate and manipulate video content in really powerful ways.
Okay, lots of exciting avenues. So just to sum it all up then, Generative Blocks World really feels like it delivers a powerful, much more intuitive and incredibly granular way to interact with and edit AI-generated images in 3D.
I think that's right.
This kind of precise structural control seems absolutely crucial, doesn't it, for AI researchers, for ML engineers, anyone really pushing the boundaries of creative AI models, maybe even building tools for synthetic data generation.
Absolutely. The key advantages are really clear. You get that precise geometric control through these manipulable primitives.
The AI Legos.
The AI Legos. You get superior texture preservation, thanks mainly to that innovative texture hint and confidence mask.
Right.
And you get that incredible flexibility to edit across different levels of abstraction, from broad object movements right down to fine-grained details using the variable K.
Yeah.
It really feels like a significant leap forward in making these amazing generative AI outputs not just beautiful things to look at, but things that are truly editable, controllable, and practical for real workflows.
So the final thought maybe for you, the listener, what does this all really mean? Consider how this new ability, this power to reliably control and edit generative output in 3D could fundamentally transform workflows. Think about 3D content creation, visual effects, maybe even how we create synthetic data for training other AI models. How might these abstract yet deeply functional AI building blocks influence the next generation of creative AI tools, the ones that maybe you will build or use? It's truly a fascinating development, and it definitely unlocks a whole new range of possibilities.